Hello. Today we will continue our lecture on RNN, recurrent neural network. So we're gonna first introduce a couple of different architectures, different RNN architectures. Okay, so these different types of architectures, they are suitable for different tasks. Okay, I think I mentioned a bit about how the model is different depending on the output, depending on what kind of output we want, right? So we have already used the example of named entity recognition, in which we need an output for each time step. Okay, so this is a very typical many-to-many architecture. So we have many elements in the input. So the input is a sequence and the output is also a sequence. So that's the so-called many-to-many architecture. And we're gonna see several other types of architectures. All right, okay. So in this first type, many-to-many architecture, we have the inputs X, which is a sequence, and the output is also a sequence. So this is a very typical structure architecture for a lot of the natural language processing tasks. For example, we know the named entity recognition already, and there's also a well-known task called part of speech tag. Okay, so the part of speech tag task is basically to label the functioning roles of all the words in a sentence. Okay, so like we like to know whether this word is a noun or verb, or whether this phrase is a noun phrase or verb phrase, and so on. Okay, so it's more like a syntactic analysis, but this part of speech tag requires that we need to give a tag to each word in a sentence. Okay, so that's, if we think of this task more carefully, then the role or the syntactic function of a word actually depends on its context, right? The words in different positions of a sentence, even if it's the same word, it can play different roles depending on which part or which position that word is within a sentence. Okay, so a good part of speech tag model should able to incorporate the information in both the left side and the right side. That is the word before the current word and the words after it. Okay. So let's look at the second type, which is many-to-one. Okay, so I think this type of architecture is it's much easier to understand because the output is just a one variable or one quantity. So we want to basically summarize all the information within a sequence. If the input sequence is a sentence, say, or a short paragraph, it could be a review of a movie, it could be a review of an item, and then the output score could be a continuous value, that's a real number value that indicates the quality of the item or the overall score of a movie. Or the output could be a binary or discrete outcomes, say the different types of sentiments. Okay, so this is easier to understand compared to the many-to-many architecture. And if we look at the models, the architectures here, you'll see that there's no need to to have an output for each time step. Okay, so all we need is to let the first word or the first element be the first input, and we'll take the outputs from the first time step and we will reuse this activation from the previous time step in the next time step. So this history information, the information encoded in the first word is passed along. Let me use another color. Is passed along through this activation to the second time step and passed along further to the third time step until to the last time step. So that means if we use the activations from the last time step, okay, so this A capital TX, the activations from the last time step, it not only contains information about the last word, movie, okay, but it also contains all the information from all the previous words, like everyone should go to theater to watch the movie, or everyone should not watch the movie. So all the words in the previous part of the sentence are kind of accumulated or passed along to the activations in the last time step. And this last time step activation is kind of a condensed representation for the whole sentence. Okay, so so that's why sometimes we just call a neural network model, a recurrent neural network model to be we use a different name like sequential neural network, sequential neural models, and so on, because we model the information sequentially. So that's the second type of many-to-one architecture. And now let's look at the third type. Okay, so it's just a flip around of the many-to-one. It's one-to-many. Okay, so we can notice that there's no inputs for the different time steps here after the first time step. We just use one input element, and we use that to generate some outputs y hat 1. Okay, so this particular architecture is used to in tasks, for example, music generation or natural language generation. Okay, so the state of arts natural language generation models that were in the field of natural language processing, we would say it is the GPT model. So we have GPT first came out in 2018, and in 2019 we have GPT-2, and this year we have GPT-3. And these GPT-2 series models are huge models, and they are kind of different from a simple recurrent neural network based models. But these GPT models, they are not based on recurrent neural network, but the one-to-many architecture are similar. The difference is that how we come up with the activation representations. Okay, so in the future lectures after recurrent neural network, we can spend some time on these more complex models. Okay, but the model's architecture are basically the same. We just use the one input to generate the rest of the outputs. Okay, so you see that we have y hat 1 here. So this y hat 1 is used in the next step. We don't require external outputs at time step 2. We just use the prediction from the previous time step to be used as the input for the next time step, and then we generate some y hat 2, and y hat 2, which is the second generated word, will be fed into the network to generate the third. Okay, until we reach some points. Okay, we have a satisfactory ending word generated. Then that's where we cut the model and say, okay, we're done with this generation task. Okay, that's the one-to-many architecture. Okay, so the last type of architecture is the many-to-many case, but the length of the input sequence and the expected output sentence, they are different. Okay, say given the input sentence that has 3 words, then I probably want a same I want the output sentence to be of different lengths, because if the task is to translate the sentence into a different language, then that second language may require different number of words, right? Depending on the grammar, depending on the specificity of the special places of the second language. Okay, so in this case, the output length is not necessarily the same, matches the input length. For example, here I translate the Chinese sentence into a English word, into an English sentence. So the English sentence requires 4 words, but here I have that many 7 characters basically. So if the model handles each character as an input unit, then of course these two input lengths and output lengths don't match. Okay, so this task is most commonly used in machine translation. Okay, and this type of model is also known as sequence to sequence model, because it is a mapping between two sequences. Okay, so in the future we will talk about the sequence to sequence model, but with different encoders. So here our recurrent unit is the encoder. Okay, but in the future we will see that recurrent encoder is not the most performance unit, but the paradigm provided by the many-to-many recurrent neural network is still being used in research and in production. Our if you open up your Google Translate app or any other translate app, you can speak a sentence to it and it will generate a target language. So that is a very typical usage of the sequence to sequence model. Okay, so there's basically 2 steps involved. So on the left step, this is the encoding step. So this step, you can think of it as a many-to-one encoding step, because it summarizes all the 7 characters in this sentence into one condensed representation, this activation at tx. So this is the condensed representation of the source sentence. And this condensed representation is fed into the second one-to-many decoder component. So this activation will be used as the initial activation to decode into the sequence of a second language. Okay, so this many-to-many is basically kind of a combination of a many-to-one encoding and a one-to-many decoding here. All right, so that's the typical 4 types of RNN-based models. So I think next, I'm going to use a concrete example from language modeling to showcase how RNN-based models work. Okay. So a language model is an important task in natural language processing in general. Okay. For example, in the application of speech recognition, the task is to receive an audio wave data and to convert it to text. Okay, so here, when we do the conversion, we basically need to do a lot of disambiguation. So like we want to clarify at a certain point that the most likely word, the most likely next word could be this word A as opposed to other choices. And this is where the language model will be used. For example, in the sentence, 2-sentence example here, the above one, on the wall, I see a picture, right? And the second one, it sounds very similar to the first one. On the wall, I see a picture, okay? But that doesn't make sense, right? That is less likely than the first sentence, because in most cases, we see a wall, we look at a wall, we'll see a picture, not a picture hanging over there, right? So because the word picture and picture, they sound very similar. And when we use a speech recognition software, it doesn't have any context about whether the sound picture or picture should convert it to which word. It doesn't know that. We we will need use a language model to tell the speech recognizer that, okay, in this case, the picture is more likely because I have heard on the wall, I see a such word before the sound picture, okay? So that's why I think picture is more likely to be the next one. So that is basically what the language model can achieve, okay? For example, given the language model, then we are able to output the probabilities. So the capital P here indicates the probability of a sentence. So probably in this case, the probability for the first sentence is that many number 5.2 times 10 to the power of -2, which is a very small value, but it is still much bigger than the probability of the second sentence. So then we can prefer over the first sentence, first sentence over the second sentence. Okay. So in general, a language model should be able to output the probability of a sentence or of a sequence of words based on its experience from a large, from its training, from the training process, based on large corpus. Okay. All right. Now let's look at the example of how a neural network-based language model is trained. Okay, so I emphasize that here, an RNN-based model can be used to train a language model. And yes, the probabilities are basically the word at each position is the results of a softmax output layer at each time step. That's correct. Okay. So I just said we can use RNN to build a language model, and we will see in 2 slides later that at the beginning, when we don't apply RNN a lot, there's a technique called Ngram language models. So that Ngram language models is still kind of a decently good baseline models, but nowadays it's outperformed by neural network-based models. Yeah. All right, let's look at this example. So first, we need to collect a large body of corpus data, textual data to train the model. Okay, so for each training example, it's a sentence, and we need to tokenize first. That means we need to extract all the words from a sentence. So on the wall, I see a picture, then we tokenize everything, right? And we sometimes, in most cases, we will need to append a end of sentence token, a special token here, because we want to know where the sentence ends. And sometimes we also include a start of sentence symbol, okay? But that is not very often commonly used in RNN-based network language model, okay? All right, then after we tokenize it, then we can have the indices for each word in the vocabulary, right? Remember that in the example we shown in the previous lecture, we need to collect all the possible unique words in the training data. That is a very large quantity. Say we can usually have tens of thousands of words in our training data sets. And so that each unique word is assigned an index or a word ID, okay? So in this case, we have the article A, and the article are usually the most frequent words in the corpus. So we just assume that, okay, so this is the words that has the index 1, okay? So that's our assumption. So all the other words are associated with an integer number that indicates the index in the vocabulary. Okay, so let's look at the one training step. Okay, So I listed the vocabulary here. It is 10,000 unique words. All right, so at the beginning of the task, we don't have any context information, right? We don't know what the first word is, so we can like use some arbitrary input. Say, let's just use 0 index as the first token, input token, and the activations is also initialized to 0. So that is something we can randomly choose to initialize the model. Okay, so given these initial inputs, we can have the y hat 1, which is the prediction for the first word. Okay, so y hat 1 look like this because it is the outputs from the softmax layer, and the softmax layer has many. It's basically a vector of probabilities. Because the vocabulary size is 10K, so the outputs y hat 1 is also a vector of 10K elements, and each element indicates the probability of what the first word is. Okay, so the probability of being a, being about, or being on are all listed here. So this is the prediction of the model. It's y hats. Okay, so and because it's the training step, we need to compare this prediction y hat 1 with some ground truth, right? So the ground truth is y1, and y1 is a 1-hot encoding, right? 1-hot encoding of the first word on. Okay, remember 1-hot encoding. The vector y1 is also of vocabulary size elements, and there's only one here at the index of the word on. Okay, so we need to compare this one hat one, the y hat 1 with the ground truth y1 using the loss function of softmax regression. Okay, remember the loss looks like this. We should summation a bunch of products, which is y hats, y1 times the logarithm of y hats, right? And because we have 10K elements in a vector, so we should sum up 10K of such products and give a negative symbol here. So that is the loss of the first step. Okay, so given using that loss, we can able to compute the gradients for the linear activations, the weights in a network, right? So the DO is actually the kind of the DZ for the output layer for the W's here, WA here. Okay. So the gradients is simply the difference between the y hats and the y. So this is something we already know why this is the case in softmax regression. Okay. So next is kind of tricky because we have predicted the first word, right? And we've got some loss. So we will need to use the activation from this first step to predict the second word. Okay, so this time the input to the model is the first word because we want to predict the second word on top of the first word. The first word will be our context, right? Language is sequential. We should not predict all the words independently. We should predict the next word based on our knowledge on all the previous words, right? So the activation is passed along here, and also the first word y1 will be used as the input for the second time step x2. Okay, so this is the inputs for the second time step, and we will have some predictions y hat 2 for time step 2, and y hat 2 similarly. It is also a bunch of probabilities from the softmax layer. But the nature of these probabilities, they are conditional probabilities because we know that the word is already the first word. Okay, so this y hat 2 will be compared with the ground truth y2 again to get some loss to update the parameters. And the y2 is the word the, okay, which I didn't list it here, but it's straightforward to see that we'll need to compare this y hat 2 with the y2. Okay, so in the next steps, what we will do is similar to the previous two steps. The activations will be passed along, and the inputs for the third time step will be the second word, the, right? And some y hats 3 will be computed, which is the probability of the third word given the first two words being on the, okay? And until we reach the last step, okay? And we will use the seventh word picture as inputs, and then we will compare the y hats, a bunch of vectors, a bunch of probabilities with the last token, which is the special end of sentence token. Okay, this end of sentence token also gets a 1-hot encoding representation. Okay, so that's basically how we train the neural network model given a input sentence. So that is typically how we train neural network, recurrent neural network based language models. Okay, so the training is takes a lot of time because the backward propagation is back propagation through time. It is typically slower than a regular network, and also the sentences are of different lengths, right? In your training data, we can have short sentences and long sentences, so that makes the training more costly because in order to input multiple sentences, to put multiple sentences into a mini batch, then, for example, the first row we have 4 words, the third row we have 6 words, and the last row we have 10 words. So how do we make a mini batch that's fit into the same matrix, fit into the same tensor? We need to get some paddings, right? For those short sentences, we need to pad the rest of the sentences so everything can fit into a tensor. So that paddings and other tricks makes the training more costly. It'll cost us more, usually cost us more computation time than a regular network. Okay, and also depending on the nature of the network, it's a recurrent network. So the backprop is not a very efficient one. So usually training a recurrent neural language model is not a very efficient one. Okay, it'll cost you a lot of time. Okay, so now let's look at, given a model trained, what we can do with the trained model. Remember, in the audio recognition task, we want to use a language model to output the probability of a sentence, right? So now we assume that we already have a model, and also we have a new sentence which has 3 words: I, love, and you, right? And we want to use a model to estimate the probability of such a word, right? We want the model to output something, okay? And that is also straightforward. So first, the input is still x. The first input is still 0, right? Because we need to start from nothing. We will start from the blank, right? Before we start sentence, we don't have any context. So the first input will be 0, and the first activation will also be 0. So the first prediction, y hat 1, is a bunch of vectors, is a bunch of probabilities. Okay. Now these probabilities, they contain the probabilities for all the words in the vocabulary. Okay. So in which we can find, in which we can find the word for I, right? I listed I here. So among the prediction of the first time step, we can always find the word I, okay? And in the next time step, here we use the first word I as inputs because we want to predict the second word. So this y hat 2 also contains a bunch of probabilities, which are the probabilities of all the words in the vocabulary given the context word I. Okay, so within it we can find the word, the probability of love given I. Okay, and the third step is to find the probabilities of the third word given the first word I and love, right? We can easily identify the spots the probabilities for you given I and love. Okay, so all we need to do is to take these three probabilities out. Okay, because we can apply a simple mathematical rule, which is the chain rules of probabilities. The probability of a sentence is the probability of the first word times the probability of the second word given the first word, and the probability of the third word given the first two words, and so on, right? No matter what the length of your sentence is, you can always carry out these chain rules by multiply a bunch of probabilities together. Okay, so this is the result. What we will get is the joint probability of a sentence. It's basically the product of all the conditional probabilities of all the tokens in a sentence. Okay, so now it's time to estimate the probability, and the best language model should give the highest sentence probability on unseen test data. So that is a principle we use to basically measure the performance of a language model, right? Because we can have different language models that have different architecture, different parameters, hyperparameters, and also trained on different text data. So when we test a language model, we want a language model to predict the highest sentence probability, okay? And in practice, we use the term perplexity, which is the reciprocal of the sentence probability, okay? And this perplexity is easier to read because it converts a very small number probability into a relatively normal number to read, okay? So that's why we use perplexity to indicate the performance of a language model. And because it is the reciprocal of the probability, we want the perplexity to be small. We want the perplexity to be as low as possible, okay? So a language model that predicts, that has overall lower perplexity scores are the better ones that we want, that we wish to use, okay? And to maximize probability equals to minimize the perplexity, okay? So in the application of language models in audio recognition, we are applying the language model in the decoding step, okay? So the audio waves are encoded into some vector-based representations, and these representations, big O's, are used to decode into a sequence of words. So let's look at the example here. For example, the audio segments that the software reads is pair, right? We know there are two pairs, but we don't know which pair should be the case. But given the history information, given all the previous words, I like to have some apple and, right? So the language model will take these previous words as inputs and given and the outputs, the probabilities of the next word to be pair versus this pair. So we'll see that the probability of detecting a fruit pair is much higher than producing the second pair. So that's why the audio recognition software will prefer to produce the fruit pair. Okay, so the same example can be applied to the on the wall. I see a picture versus the picture. Okay, although even though they sound similar, but we can use the history words or the contextual words to predict the next word. All right. That's the application for language models. So now, as I said, before we use RNN-based language models, there's a very mature technique called Ngram language models, which is also, I think it's still worth knowing. It's worth to spend some time to know about what it actually does. Okay, so it's basically to estimate the probability of words by counting the frequencies. Okay, it's a simple technique. So on the wall I see is a sentence we want to estimate, and we can use the count of this phrase on the wall I see a picture divided by the counts of this shorter phrase on the wall I see as an estimation for the probability picture given on the wall I see. So this makes sense, right? We use the number of appearances of the context as opposed to be divided by the occurrences, number of occurrences of the whole target sentence. Okay, so in order to use a Ngram model, we require very large corpus, because if your corpus is not very large, then the likelihood that these very complex, very long phrases can only appear once in a corpus. So we want the same words to be repeated for a sufficient amount of times. Okay, so the probability of the sentence is also decomposed into the combination of the probabilities of words based on the chain rules. Okay, so for example, here we have the first probability is the probability of word on based on S. S is the starting symbol. Okay, the /S is the ending symbol. So times the probability of the times the probability of war. As you can see, the context actually grows, and the last probability actually relies on all the previous words. So in practice, this very long context is not achievable. Okay, it's not feasible, because for long sequences, it's not likely that we can observe more than twice, or to observe the occurrence more than twice, right? So we need to use some way to approximate the context, okay, because it's too hard to estimate. So the simple thought is that we can reduce the length of the context. We use less context words, right? We just look back, for example, look back for only one word. If we only use the previous one word as a context, then we will have the so-called bigram language model. So the probability of word on conditioned on the starting symbol is the count of these two phrases divided by the count of starting symbol, right? So that's one estimation. And the probability of word the is the count of on the divided by the count of on. Okay, so we just use the one word as the context, not all the previous words. And the last word picture, the probability of picture is also contextual, conditioned on the one previous context word, which is a. Okay, a picture, right? Divided by the count of a. Instead of to go back to see the I to the word see, I, or, and so on. Okay, we use much shorter context. Okay, so in this time, the probability of a sentence is just the product of all the short bigram probabilities, and we use the same chain rules, and this assumption is called Markov assumption. So you must have heard this term in a lot of other courses. So it's basically a phenomena that we say the probability of the future events depends only on the previous, on the immediate previous the immediate previous events. We don't trace back to the further histories. Okay, so this is the case for bigram. Okay, and of course we can trace back more to look at the previous two words, and that'll give us the trigram, right? If we look at the previous two words, then the probability of the word on should be counted, by counting the occurrences of this phrase and divided by these two starting symbols. And the word the should be counted by the phrase starting symbol with on the, right? Divided by the count of starting symbol and on. So the context increases by one word. So that in theory should give us more accurate estimation of the probabilities. And this is the so-called Markov, trigram language model. And the context extends from one word to two words. So in practice, when we want to develop some really accurate Ngram-based models, then we can probably use trigram at least, or quadrigram like 4 words, or pentagram like 5. But we usually use 4-gram or 5-gram to indicate those longer contexts. Okay, so the advantage of these Ngram-based language models is easier to train, right? It's not neural network. There's no back propagation needed. We just need to count all the occurrences. So it's much easier to train, much faster to estimate. But the big advantage is that it is unable to capture the long-term dependencies. Okay, it is unable to capture the relationship between the current word and the word that's beyond the context window. Say the word picture here, right? Why we use a picture here is partially dependent on the word on, right? So on the wall, I see a picture. But if the word is, say, in the wall or behind the wall, then the word is less likely to be a picture, right? So that said, the future words can have long-term dependencies on the beginning of the sentence, right? So that's why the short context used in an Ngram language model sometimes can fail, right? Because if I only model the first, the 3 words that's before the current word, then I can only see these 3 words, I, see, a, right? So these contexts are not sufficient to estimate the probabilities of the next word. So we want a language model to be smart, to be intelligent enough so that the long-term dependencies are captured. So that's why we will introduce the gated recurrent units in the next lecture. Okay. All right, so let's advance to the next slide. So it's furthermore, comparisons of RN-based language models versus the Ngram language models, as you can see here. So all the rows above are Ngram-based models. So in terms of perplexity, so the perplexity is just the probability measurements. It measures the performance of the language model. We can see that the neural network-based models have lower perplexity score, which means they are more accurate in predicting the word probabilities. But also in terms of training times, it's significantly larger, right? So if we use recurrent neural network-based models, the perplexity, the training times are basically, it could be 100 times larger than Ngram-based models, right? And also the number of parameters is also much larger. It requires more advanced computers, larger memory space, and very performant GPUs to train the models. Okay, so that's RN in language modeling. So if we look at a language model, what a language model could do, it can help with the sequence generation. Okay, so for example, when the language model is trained, we can use some initial inputs to generate the first word, right? We have seen this in the previous example, right? So we have y hat 1. So we can randomly sample from this distribution to generate some sentence from scratch, right? For example, if we sample the first word to be the, then we can input the to the second time step and then generate a second word. Okay, so given the, we can have a second distribution, and then we sample we can take the most probable words, for example, the president, right? And then feed the second word president to the third time step, and we can have the third word is generated, and so on until we reach the point where the end of sentence is generated. So that's how we generate some sentence from scratch, given no information, right? So that is some interesting task a language model can do. We can basically generate a random sentence by randomly sample the starting words from the generated distribution. Okay, so other than natural language, the language model can even generate different genres of text. Okay, so people have tried this, like generates a Shakespeare-like writing, like we first need to train the language model on Shakespeare's all of Shakespeare's work, right? All the novels, all the plays, and then the model will be used to generate some random paragraphs, random sentences, even random people's names. And it all looks very pretty similar from a first glance, although the whole paragraph maybe doesn't make any sense at all. Okay, and also people even tried this to generate academic writings, and all these writings are learned from LaTeX source code. Okay, and it almost compiled because it's learned. The RN language models can capture the syntactic dependencies in the LaTeX source code. So this are two interesting piece of articles that you can look at through this blog, and the author of this blog wrote a lot of famous tutorial or introductory level introduction posts to the recurrent neural network models. Okay, and it can even use to generate source code. Okay, so I think on the left it's the C++. Both sides are the C++ code generated by it's actually C code generated from a language model, and that language model is trained on actual source code. Okay, and it is able to generate some functions, like these function names in the really pretty authentic style, right? Indicate policy, and it has for loops generated, right? It has if else branches generated, and the return is also generated. So it's quite interesting, but I'm wondering whether this code can compile or not, right? Not sure nowadays what the state-of-art model can do to source code generation. Okay, and at least we don't expect a model to generate meaningful source code from totally from scratch, but this kind of technique is helps software developers to faster decode, faster debug, or to faster produce code. Because while we type in the modern editor, say VS Visual Studio Code, then we can have plugins to help predict what your next word is, what your most likely fill up word to be. Okay, so these techniques are already used in production. All right. So finally, let's look at this slide. So it's a character level language model. So all the language models previously we introduced as examples are word-based, right? We first need to segment a sentence into a couple of words. But because in the European languages, all the words are composed of letters, of alphabet letters. So we can basically use a character level language model. So each time step, we use one character instead of one word. So the advantage of this character-based model is that, okay, we can deal with the unseen words. It's okay if in a testing set, in a new sentence, it's okay if the word we have never seen it, but as long as all the letters we have seen it, then we're okay to compute the probabilities for a totally new sentence, right? So in this case, even the blank space are used as inputs because it also represents a letter. Okay, so this vocabulary can be much smaller size than actual words. Okay, so it's much easier to deal with the out of vocabulary words, like given like for example, unseen people's names, unseen organization names. It's much easier to estimate the probability. Okay, and also the sentences are much longer, so that means your current neural network should take care of much longer inputs, which means they are more computationally expensive. Okay. All right, so that's so much for the lecture today. And from the next lecture, we're gonna talk about how to deal with the challenge of capturing long-term dependencies by introducing the gated recurrent units. We're talking about two types of networks: gated recurrent units, GRU, and LSTM, long short-term memory. And the LSTM is, I believe it is most frequently used variants of gated recurrent unit. Okay. And also, we'll quickly cover the bidirectional RN and the deep RNs on top of the LSTM and the GRUs we introduced. Okay, and that's the lecture for today. If you have questions, you can let me know. And also, I will release the quiz questions later.